Good day, friends. Welcome to today's tutorial. Today we want to concentrate on this frame which we did in our last video on the bending moment, shear force and normal force of this particular frame. All right, so today we want to continue from here. Remember, we've already drawn the bending moment diagram, and we can see the bending moment diagram on the board. Now, the next phase is the determination of the shear force of this frame. Now, the first thing we are going to do in doing the shear force, we must understand that the shear force normally acts perpendicular to the member. In other words, the shear force acts transversely to the longitudinal, to the span of the member in question. So, we are going to start with member A, D. Okay? We have A, B, C, D. Remember this C, this D. So we're starting with member A to D. So let's draw it out. We have this is member A to D. There's a point. We have a load, which we have our reaction 218.92 kilonewton. We have a horizontal load of 50 kilonewton. We have 50 kilonewton load acting. Now remember, these are point A to D. Now for this place, if we discretize this function, we are still going to have a reaction coming this way. And this reaction is 18.92 kilonewton. We're equally going to have a horizontal load here, which will be equal in magnitude to this. Okay, so this is what we have for this particular beam. Now, the next thing we want to do now is to obtain the shear force. Now, if this is our AD, the shear force at the force to produce shear is expected to act perpendicularly at this point. The shear force, the force to produce shear is expected to act perpendicularly. So, in terms of the 50 kilonewton load, this force is expected to act in this way. Now, in terms of this support reaction, let's draw another value for shear. Okay, so we are going to be seeing now, we are seeing two forces. When we take this plane, let's draw the plane. So this is our plane of interest. This is our plane of interest. So if this is the plane of interest we're interested in, we have this. Let's call this one FA, and let's call this one acting as a result of this. Let's call it FA prime. Okay, so we can clean this off so that we'll have a clearer picture of what is transpiring in that plane. All right, so this is what we have. All right, so the next thing we want to do is remember that we have this as our horizontal plane, our initial horizontal plane, and we have here to be, we've gotten here to be 5, we've gotten here to be 4 meters, 5 meters. Okay, so the next thing we want to do is to first of all determine this angle. So let's call this angle theta 1. So let's determine theta 1. In doing that, we are going to have it, I'll write it here, tan theta 1 is 5 over 4. So theta 1 is tan inverse 5 over 4. So we have our theta 1 to be 51.34 degrees. Okay, so that is our theta 1. Okay, now like I said that the shear force acts perpendicularly to this point, meaning that this angle is 90 degrees, okay? So if we have this, we already know this 90 degree. The next thing we are going to find out, we are going to work on, if we decide to split to get a vertical of this, if we take a vertical of this, if this is 51, what it means, if it's 51.34, it means here will be what? 38. Okay? So I have 38.65. So here becomes 38.65 degrees. And if here is 38.65 degrees, here automatically becomes our 51.34 again. All right? Now, this force FA is the resultant force acting on that point. So what it means is we can now is the resultant force. So all we need to do is to take a triangle, all right? Represent this as the triangle, okay? So if we do that, we can have that all right, so we have our FA. So here becomes 51.3. So if here is 51.34, of course we can obtain this knowing fully well that here is vertical. So here we are going to have 38.65 degrees. So that is what we have here. So let's say we have here to be 38.65 degrees. Okay. So this becomes our resultant. So if this is our resultant, FA, which represents 50, yes, 50 kilonewton. If it becomes our resultant, so we are going to be picking from this point here. Okay, so we'll pick here. Here becomes our angle 90. This becomes our resultant. Okay, so FA becomes the adjacent. This becomes the hypotenuse. So we can say conveniently that considering this one, let's call here B. At this point, here is our AC. So considering B, A, C to be 38.65. So from BAC, we call here our C. We can say that FA becomes, or let's go this way, we can say that cos 38.65 degrees is equal to adjacent, which is our FA over the hypotenuse, which is 50. So we can say that FA becomes 50 cos 38.65 degrees. So work it out and look for what our FA stands for. So what was 39.048 kilonewton. Okay, so this is the force acting perpendicular to AD. All right, so this is the force acting perpendicular to AD. Then the next thing we are going to look for is this force also acting perpendicular to AD, and this is the force due to our support reaction, which is 218.92. So if this support reaction becomes our resultant, like we know, we can take the point, these are angle 90. We do the same. So this becomes, we look for this angle similarly. So now let's look for this angle. We have this. We have here this 51. So here we have here to be what? 51.34 degrees. So if here is 51, here is 36, means from here to here will be what? 38.65 degrees. And if here is 38.65 degrees, it means this angle here to here becomes 51.34 degrees again. So all we will do now, we'll say adjacent, which is, let's call this one F. We've already labeled it, we'll call it FA prime. Already labeled it as FA prime. So this point, this angle, this force, which is perpendicular to this member at 90 degrees, is our FA prime. All right. So now let's look for the FA prime. Similarly, we will say cos 51.34 degrees is equal to adjacent FA prime over hypotenuse 218.92. 6.758. So we have 136.758 kilonewton. All right. So this is what we have as the FA. Now, this force, we know that we have two opposite forces. Of course, we are going to determine the resultant forces as a result of these two forces in opposite direction. Now, assume the forces coming to be positive, while the one coming down is negative. So if we do that, we're going to have this minus this. So we have resultant force. Let's call it resultant shear. Shear force becomes equal to 136.7588 minus 39.048 kilonewton. So if we do that, the resultant shear becomes equal to, let's work it out, minus 97.71. So we have 97.71 kilonewton. So this is the net shear force acting at this point. Of course, we know how to take shear force. So once it be the net shear force, this force will act. We don't have any other member, any other load on this member. So that this force will act till it gets to this point. All right. I haven't gotten the shear at this for this member. Let's draw it out. Let's see. All right, we are done with the first one. So quickly, let's look at the next member. All right, so the next thing we are going to do is to consider the cantilever portion of this frame. So quickly, if we take the cantilever portion of the frame, we are going to have it as this. This is the cantilever portion, and this other portion again, we have the next portion to the footer, which is this portion. Okay, here we have the support. So first of all, let's look at the cantilever portion of this frame. So analyzing the cantilever portion, remember that the load is 30 kilonewton. Here we have here to be 4 meters, and the axial force will be represented. So definitely we'll have an axial force which will be opposite, which will be acting towards this direction. All right. That axial force will be acting towards this direction. Remember that when we drew the first thing, we have a resistive shear like this, a resistive horizontal load. Here was 50 kilonewton, meaning we are going to have here to be 50 kilonewton under equilibrium. So if we have here to be 50 kilonewton, it means for these two, we are going to have another force acting here, which will also be 50 kilonewton. That force will be acting axially to the member. Okay, so that force automatically becomes the axial force, which is the normal force on this member D to C. So let's not go into that yet. Let's start with the shear. Now for this span, for this cantilever portion, will be becomes D prime will be 30 times 4. That gives us 120 kilonewton. So a shear of 120 kilonewton starting from this edge of the cantilever is going to continue to the support. Okay, so we have that. So if we want to draw the shear, we will now say we have that shear, it will move continuously to that portion. Okay, just as we've gotten for that of the slant side. Now this other portion, we are going to deal with it separately also. Now let's look at this portion. This one is the shear for this portion. Now let's light of it. Now once we've gotten the shear, and we know that our RD prime is 120 kilonewton, here also we have a reaction. All right, we have a reaction. So if it's going to have a reaction, remember, let's call that reaction RDC. Let's call it RO. Why we call this one RODE. Let's call this one RODE. Let's call this one RODC. All right. So these are the two reactions. Now RODE, which is the reaction due to the cantilever, and RODC, reaction due to the other span of the frame. So remember that the total reaction, which is opposite in direction to this, was coming down. When we draw the slant side, we have it to be 218.92 kilonewton. So what it means is that this summation of these two forces must be equal to what? This. So remember, this is 120. So we can easily obtain the other one. So we can say that RODC is 218.92 minus 120. So RODC becomes 218.92 minus 120. RODC has given us 98.92 kilonewton. So that gives us the shear for that particular portion. Okay, so haven't gotten the shear for the portion, so we can conveniently remember we have a UDL here. So why this is 120, this is 98.92. So we have a UDL here. So if we want to draw the shear force, it starts here. Because of the UDL, is going to come down to somewhere here. Okay, so if we work it, if you want to do it, so if we consider the span DC, so if we consider span D to C, we're going to have it like a beam. We'll have it this way, the shear. You have the support at 98.92. You have a UDL, and you have another support here, which we do not know. Of course, the only way we can do it, we can just, once we get this support, we've gotten the position of the shear at this point. Or you can say 98.92 minus, we have here to be 30 kilonewton per meter. So 9830 times 10. Remember, here is 10 meters. Okay, that's 10 meters. So this gives us also the reaction RO. Let's call it RCD. That gives us RCD, which is representing our shear, gives us minus 201.08 kilonewton. All right, so that is what we have for the shear at that point. So we want to draw the bending, the shear force diagram, it becomes, and we know that the shear is going to take a rectangular format. So it's going to go straight like this. All right, so the next we are going to check out for the shear for the other side, which is span consider span CD. So let's consider span CD. All right. Now remember I told you that we have an axial force that was acting here, which is equivalent to our axial reaction. So I don't want to draw it here so that I won't complicate the drawing. So I just want to leave it that way. So definitely the axial force is acting here, which it automatically represents some sort of a horizontal load for the span CD. So if we draw span CD, we're going to have the axial load coming here. Remember, we have a UDA here, we have the support. Okay, we have the support. So remember we said that the shear force is a force acting perpendicular to the span of the member. So the load is here already. So that load is 10 kilonewton load. We know that load is 10 kilonewton load, kilonewton per meter load. And we know that this span is 5 meters, 5 meters span. All right. Now the shear force from that point, remember that this support, at this support, we do not have any form of horizontal. Is a pin, is a roller support, so we don't have. So this thing is more like some sort of a cantilever, some sort of a cantilever in his own guys. All right, so we are going to see what this support reaction is. We've already known is 8 is 50 because of the axial load that is acting on span DC. We already know the axial load acting there is 50, and here we have it this way. So most likely it's supposed to, here it's supposed to be 50. But if you want to check, you will discover that if you multiply this by this, you are going to have it as 50. That becomes the load for this point, which means it tallies. Okay, so it shows that it tallies. So from this point, we're going to have the diagram as this, meaning that from here down until it gets to this point, and here it becomes 50 kilonewtons. So you can see that the axial load on span DC is the same as the shear on support CD, which is, you can call here RCB is equal to 50 kilonewtons. So what we've done now, we've been able to draw the entire shear force for this. So in combination, we can redraw everything so that we can have a uniform diagram for our shear force. Okay, so let's go and let's see how we can do that of the axial force. All right. Next phase we want to work on the axial force. We've drawn the shear force. Let's go for the axial force. Now, coming back to our previous diagram, let's resolute because we're going to have our axial force. Now, the axial force, if this is our member A to D, this is our member A to D, the axial force is the force acting along the axis of the member, and it's known as the normal force. So the normal force is that force acting along the axis of the member, also known as the axial force. Now, how do we resolve this? We are going to resolve it in terms of the two components like we did for shear force. We resolve them in terms of the two components of force. Now, remember, we've gotten this, okay? We know the angles. So let's resolve this first. Starting with, we have our 50 kilonewton force here. So we needed this. We needed this to play. All right. So we needed this. So what we need to do, now if you look at these forces, Now, if you look at these forces, you will discover that this force is parallel to our axis. It's parallel to our axis. So we need the parallel forces to our axis in terms of our support reaction, which is 218.92, and in terms of our load, which is 50 kilonewton. Both of them are resultant forces. So we need the axial force acting on this direction. All right. So if we do that, we'll say that the forces here, why this one is acting this direction, we can also have this force. This is a force coming. You can see it. So we are going to work on the normal force diagram of this particular point. So let's come back as all right. So having done that, let's look at the normal force diagram. You can see on the board we've drawn the normal force diagram. So using the resolution of forces, using the principle of triangle of forces, we've been able to draw the forces like you can see. Here remains our member A. Here is our point A. Sorry. This remains our point A, yes. This remains our point A, B. Now, if you look at the AD, you look at the plane, you are going to discover that we've drawn it in such a way. We've gotten our shear force, which is FA and FA prime. So what we're interested in, we're looking at the force component of this resultant force of 50 kilonewton acting here. Now, if you draw the force vector, you can see the diagram. You can see due to this 50 kilonewton, we are going to have a force, and the force is going to be on this direction. So if here is 38.65, of course here will be 51.34, here will be 38.65, 51.34, and you look at the angle around the whole point. Okay, so if we follow it that way, you are going to discover that we draw it like this. All the arrows are pointing towards the point A. So if we resolve this one, this force in terms of the axial load, which is the force moving in this direction, we'll have it as this. We'll say the force here is adjacent. Let's call it F1. All right. If we resolve this in terms of the axial load, let's call this one F1. Then if we resolve this same force, which is a support reaction in terms of the axial load, let's call it F2, they will still be moving in the same. So we have two forces, F1 and F2, moving in the axial direction of AD. So whatever we'll get for this component of force, we'll add it to what we're going to get for this component of force to give us the total resultant normal force acting at AD. So quickly, let's do that. We're going to have this. We have cos 51.34. That gives us cos adjacent over hypotenuse. So adjacent is our F1. Hypotenuse is our 50 kilonewton. So what it means is that we have F1 equal to 50 cos 51.34, right? So that is our F1. Similarly, we are going to have that of F2 in terms of this support reaction. We are going to have F2. So F2 is the same. Adjacent, F2 becomes what? Adjacent versus hypotenuse. All right? Adjacent versus hypotenuse. Okay? So let's do that and let's see what we have for F2. All right? Or if we want to solve that, adjacent versus hypotenuse. We'll say these are adjacent. Okay, so these are hypotenuse. So we'll do the same thing like we did here. We have cos 38.65 equal to F2 over 218.92. Okay, so if we do that, we are going to have the component of force that we need at that point. So let's work it out. We'll have that F2, we'll have F2 equal to 218.92 cos, we'll have cos 38.65 degrees. Okay, so that's what we have for F2. Another way we can as well do that is to say, all right, is to use sine, because whatever force we have here is similar to what we're going to have on this other side. Okay, so that is how we we'll go about it. So let's work it out and see what we have for the component of forces for the two directions. So we'll work it out. We're going to have it as equal to, we are going to have it that the resultant normal force, is equal to F1 plus F2. So if we do that, we are going to have it as 170.97, all right, plus plus 31.234. If we do that, we're going to have 202.2 kilonewton. All right. So that gives us the normal force acting on AD. Now, having gotten the normal force in AD, the remaining normal force can be gotten because the normal force is the force perpendicular to the axial, to the axis of the member. So we can easily obtain the other normal forces. All right. Now, one other thing we didn't do, remember you can have the maximum moment for this diagram. Using the moment expression, we can do that. I want you to do that by yourself, the value for the maximum moment. All right. So now let's draw the entire diagram for the normal force. We have 31.234 for 50 cos 51. By F2, we have our F2. We have F2 to be 218.92 cos 38.65. So if we do that, we can as well decide to use sine, whichever one you wish. You can as well decide to use sine, but whichever one you use it, you are going to have the same value. All right. So let's draw the final diagram for this. Let's draw the final diagram for this. Okay. Let's start with the shear. We have the shear force diagram. All right. So this is what we have for this diagram. So this becomes our shear force diagram. Okay. So this we have here to be 120 kilonewton. Okay. 120 kilonewton. What we have here, sorry, let's try to draw to scale. Have here to be 120. Yes, 120 kilonewton. We have here to be 98.92 kilonewton. We have here, we have that point to be 201. We have 201.07 kilonewton. we have here, which is our normal force. We have here our shear force here. We have it to be 97.72 kilonewton. Then we have this one here. We have it as 50 kilonewton. 50 kilonewton. Okay, so these are roller support. Come to the axial force diagram. Now, in drawing the axial force diagram, what we need to know is that the axial force is the force that is acting. The normal force is the force that is acting as the axial force of the member. So when we are doing that, we should take that into cognizance. All right. Now remember that we have a 50 kilonewton force which is coming from this direction. So there's no other force from this direction. So that automatically produces an axial force of 50 kilonewton acting down to this point. This makes up what we call the normal force in member DC. So the normal force in member DC, we have it as this. So this value here, it goes down. It's also the support reaction of this particular member BC. All right. So this member A, this member B, C, D, E. All right. So this is the normal force here. We have here to be 50 kilonewton. So this 50 kilonewton is also acting as a support, a shear for this particular one. Now the next axial force we have is the axial force acting at this support towards the length of this member BC. So that force represents the support reaction of this point B. So we'll draw that support reaction. We know from our statics that the support reaction there was 201. So we'll definitely represent it. So here is 201.07 kilonewton. All right. So that's what we have as that force. Now let's come to this axis which we've just worked on. Member AD. We already know that the normal force here, we know what it represents. We'll have that one to be 202. So we have that force to be 202. So here becomes 202.2 kilonewton. So it acts down to this point, 202.2 kilonewton. Here is the same thing, 50 kilonewton. All right. So this is what we have. Now remember that the cantilever side doesn't have any axial force because at this junction, this was where our horizontal horizontal load acts. So there's no axial force in member ED. So this becomes our normal force diagram. Okay. So this is what we call our normal force diagram. So for what we have done so far, I believe you'll be. So for what we have done so far, I believe you're able to draw your shear force, your bending moment, and your axial force or your normal force diagram for any kind of frame. You'll be able to do that. So I believe you do enjoy the lectures. If you do enjoy the lectures, please do well to subscribe to our channels. I'll see you in our next class. Stay well.